Good afternoon, everyone, or good morning, depending on where you are. Welcome to our webinar entitled CPPS, Co-Simulation and Operational Level for HIL with a focus on cybersecurity use cases. So CPPS means Cyber Physical Power System. First, let me introduce myself. My name is Louis Raymond, and I'm Go-to-Market Manager in charge of Power System and Cybersecurity Solutions at OPAL-RT. I will be responsible for hosting this presentation today. For this, I'm glad to welcome János Csatár from Budapest University of Technology and Economics in Hungary, who will present himself and his development on CPPS and cybersecurity application in a few minutes. I also welcome Mehrdad Kazemtabrizi, who is EXata CPS product owner at OPAL-RT, and who will help us, thanks to his expertise, to answer our product questions, if any, during the Q&A sessions. Indeed, at the end of the presentation, we will allocate time to answer questions from the audience during a 10-minute Q&A session. So please feel free to send your question at any time during the presentation, and we will answer them during the Q&A session. For now, we prepare a small poll, 3 questions, indeed, just to know more about you and how you are involved in cybersecurity on power system. So without further ado, I will let answer to it before to start the presentation. Okay, so thank you for your answers. And I will let answer first. So János get to the heart of the matter and start his presentation. János, it's your turn.
Thank you. Thank you, Louis. So, in a few words about myself, I'm János Csatár, and I'm welcoming everyone to this webinar. I just wanted to tell you some things about me. So, with the Budapest University of Technology and Economics, I am a senior lecturer here, and I also received my PhD here. And my background started with network calculations, and I also worked in parallel at an IT development company, so we produce softwares regarding to power systems. And then later on, I moved to algorithmic network building and processing, and then arrived to HIL and co-simulation, building on my previous experiences. And I also has a strong interest in cybersecurity, and this is how I got here. So I have several projects with HIL and co-simulation and cybersecurity. And in a nutshell, this is about me. And let's move on to the slides. In this webinar, we will see an actual co-simulated model for cyber-physical power system that focuses on cybersecurity. First, I will begin with a short introduction of our team and lab. Then, after some briefing on the motivation and background, we will go through the details of the model and some results. Some of us working together on several projects before, and then came a cooperation with MVM, in which the lab and research got a boost, and subsequently the research group was formally founded. Today, we have around 20 members, a strong cooperation both inside the university and with external partners. We focus on delivering cutting-edge knowledge to the industry in selected areas. And from today's perspective, the interesting focus areas are cyber-physical power systems, cybersecurity, and HIL modeling and methods. Our lab was designed to be flexible to make us available the tools and the environment that are needed for the researchers to study the effects of power electronics, control algorithms, microgrids, smart grids, including the communication infrastructure and the cyber domain. Therefore, the heart of the laboratories is a real-time simulator, an OP-5707XG series, hosting various models. This could be connected to the communication infrastructure and physically to actual equipments through a P+ amplifier. Essentially, one of the features of the lab is providing hardware-in-the-loop capability for various cases, and all this makes it possible to study the cyber physical power system aspects of these devices, these connected equipment in a holistic approach. Okay, let's move on to today's topic and motivation. First, let's talk about motivation. With the Ukraine, during the last years, there were some examples or a series of incidents that affected the Ukraine power system. I think there were some webinars about that one also. And the case with the culinary pipeline showed us that an attack that does not directly attack the OT system could still lead to shutting down physical flows on a critical infrastructure. In case of the SolarWinds and Log4j, these shows us the potential threat the supply chain could pose to us. And the Vodafone Portugal case showed us that even the communication infrastructure itself could mean a threat and therefore needs to be considered. And there are, of course, many other cases that can be found on the internet. And today's topic is about an actual use case, and this has been created in a partnership with the Hungarian DSO, MVM. This project focuses on cybersecurity in a multi-hardware-in-the-loop environment, and there were some selected use cases for the demonstration of this environment. This project is about a high-voltage distribution network created in a co-simulation environment. The use case demonstrated a complete attack chain with real-life tools and high fidelity. And some of the use cases included a ransomware attack, a supply chain attack, and a made-in-the-middle attack for the 104 protocol. And today, in the next slides, I'm going to show you an actual implementation and use case with RT-LAB and EXata CPS for this specific project. We have been talking about cyber-physical power systems, co-simulation, cybersecurity, and so we need some briefing on what are those topics are for today. First of all, cyber-physical power system. In case of this, the physical power system is not only operating by itself, but it is controlled by algorithms and other tools which are also digitized and provides human-machine interfaces. And for this to work, we need some coupling devices between the physical world and the cyber domain. And after these couplers make us available the information, then the communication infrastructure and processes transmits and processes data, providing us the possibility to control the physical power system on the cyber domain. And what it means really. So let's see if there is someone attacking an algorithm inside this system control, the function of it. It means that it will not only affect the cyber domain, but it will also affect the physical system, the analog world. And this is why cyber physical systems are a little different than either the physical or the cyber system on its own. Okay, and since this interdependency between the physical world and the cyber world means that there is not really a way how to model this. We cannot simplify things too much because we are really studying what if this and that happens on either of these domains. In order to reach a meaningful conclusion, we need a high level of detail both on the cyber and both on the physical domains. Essentially, this means a digital twin to some extent. We can either create these models for offline evaluation, creating models, creating logical models, but the most accurate ones are able to run in real time. And real-time study makes us available the hardware in the loop testing, and therefore we can put actual equipment into this model and see what could happen if something goes wrong either on the physical side or on the cyber side. Let's talk about the co-simulation. You can see here there are some basic types of simulation, and co-simulation is the one where we have multiple models, we have multiple solvers, and those interact with each other. In our case, co-simulation means that the physical power system and the physical flows on the system are simulated in one model with one solver, and the communication infrastructure itself is simulated in another model with another software solver engine. And this could be also hosted on the same target as in our case. So the physical system could be, for example, simulated with RT-LAB, and the cyber domain could be simulated with the help of EXata CPS. And the control algorithms could be either on the physical side or on the cyber side. The point is that these are purely logical devices. And the connection between the two domains are provided through communication infrastructures and virtual links or physical links between the physical and the cyber domain. Let's talk more about the details. In the previous slide, we have seen the physical power system, and it is hosted on the real-time target in RT-LAB environment. This model is a part of a distribution system. There are some lines, bus bars, loads and generation, and connection to external nodes. And this is all created in MATLAB Simulink and in a compatible way with RT-LAB and uploaded to the actual model. This is an example of a microgrid, for example, and for it to operate, it needs some control which provides the power balance with the scheduled value. Then you can see that the RTUs, the functionality of the couplers, are actually implemented by Raspberry Pis. This Raspberry Pis connects with one of their interfaces to the physical power system and receives the analog measurement status signals, and also they can send back control commands and set points to the substations, to the equipment itself. On their other interface, they transmit the communication infrastructure. They transmit the communication packets through the communication infrastructure towards the control center. And these Raspberry Pis are actual implementation of an RTU. Then comes the communication infrastructure itself. It is created in EXata CPS. Here you can see this is a simplified version of a bigger communication infrastructure. The lower one, you can see those are mapped to the RTUs. So there are 5 RTUs. Here there are 5 mapped interfaces. So these are on the blue lines. On the upper layer, you can see there is another mapped device. So this is an actual interface to the simulator, and this is going to the control center. In between, there are some subnets to represent a lifelike environment. All these are connected with the simulator. You can see here. So there are point-to-point connections with the RTUs and the physical system, and with the RTUs and the EXata, and EXata with the control center. Of course, UDP communication is going through RT-LAB and towards the RTU, and between the communication center, there is 104 protocol going on. The infrastructure in the control center and for the algorithms are hosted on virtual machines. These virtual machines are created with VMware solution, and with the control algorithm running on one of the virtual machines. This is a simplified version of a microgig controller, so it balances the load to match the one that were scheduled on the system. And basically how this model is being built up. So this model is a co-simulated one, and with hardware in the loop setup on multiple interfaces, and all this work together to create a lifelike environment. There are 2 use cases, and the first one I'm going to show here is about the delay attack created with EXata CPS. So our main idea is to add some delay to one of those RTUs up here, and this would create an actual delay in the communication. So if a packet is going from the database to the RTU, or from the RTU to the database, this blue line represents the communication flow. And here, close to the RTU, we are going to add some delay, meaning that the actual information with the physical system is having a delay. And how it is all being created. First of all, you can see here the user interface of RT-LAB, and here I'm going to add some more load to load 1, and you can see the numbers here changing, meaning that we have a mismatch with the scheduled values. So the control algorithm tries to balance the system again. And now we're going to add another mismatch, another failure in the system to load 2, meaning that when I add another 1 megawatt of more load to the system, here you can see, and basically here there's another 1 megawatt step in load 2. Again, you can see the numbers are changing. So the control algorithm tries to balance everything, and up until this point, it successfully does this, meaning that it needs to only use new set points for the generators and nothing else. And since we are trying to create some more extreme scenario, we are also trying to add more load, and this is what you are going to see here shortly. And pay attention that after we are having more on load 5, then it will create a chain of reaction. Okay, so here we are going to add 1.5 megawatts to load 5 here, and shortly after you will notice that the numbers are going, and not just the numbers are going, but here it will change one of the circuit breaker statuses. Shortly I'm going to show that here. And since the circuit breaker status is going to be changed, that means that the load itself, so load 3, let's pay attention there, it changes the value right now, meaning that load 3 is now has been switched off. So the only way to keep the balance for the microcontroller is switching off load 3. And now you will see that the balance is again going to normalize to some extent, of course, with the addition of switching off load 3. And we are going to also add some delay here. So in EXata CPS, you can see the communication is going on. These are the map devices, and on one of the RTUs, we are going to add an attack, a modified packet attack type. So this means a delay is added to the system. And since we exactly know that this communication is going through a specific port, we are going to add delay to this port. Not much, just a little bit, to be not too suspicious about, for example, some CM system or other things. So this is not much. But the point here is that this actually changes the behavior of the system. And since now we have been added this, you can see we can move back and create another incident in the scenario. So we are changing the set point, the imbalance for the system again, and this one needs to be balanced by the control algorithm. Okay, and now you can see the results of this. On the top, you can see the case without an actual delay. Here you can see the switches, the 3 switches, and the 4th one, which was initiated by the control algorithm. And in every case, the power balance against the scheduled one are kept returned to their normal values. So there is a switch here. The imbalance is going to be balanced. Another switch, and this cannot be balanced by the generators alone. So therefore, the control algorithm issues a switch off for load 3, creating an opposite direction of change in the power balance. But this can be now taken back to the balance it needs. And after we remove this unbalance, then the system again, through some switching, can return to normal. And let's see what happens when we add some delay here. At the bottom, up until this point here, these are the same, so there is no delay added. Here, from this point on, we have added some delay. The additional delay in sequence is the cause of actually adding the delay in EXata, but the rest should be the same. And here you can see the effect of delay. So whenever there is a switch event, so again, remember we have changed the set point, there is a step in the power balance which needed to be taken care of. Here you can see that the control algorithm tries to create the same steps as with the normal case, but everything takes longer. And although we have added just a few hundred milliseconds of delay, you can see that the actual response of the system has been pretty slowed down. Here we can also not see the finish of this event, although the results here shows us that these steps are out of bounds, like in the upper one, but this can be long enough for some protection to kick in, and this really could have an effect on an actual system. Now I'm going to show you another use case. The important thing here is about the man-in-the-middle attack, and that the fact that it takes effect on the same network, on the same environment as before. So we have done no modification whatsoever on the model in EXata or in any part of the model. So this is really the same model that we used for the delay. The delay was relatively easy to add and to study. Now this man-in-the-middle position is being achieved with actual tools in the model, and let's go through quickly of this. So we are trying to reach a man-in-the-middle position here at the router. We are going to brute force our way to the router. We are going to upload some actual script that was created by us, and the configuration is hidden inside other generic traffic, like in our case that DNS traffic. And update is also possible. So from the point on, we have achieved man-in-the-middle position in the center. We take control of the communication flow. Let's see what we have achieved with this man-in-the-middle position. We have changed the measurement from the generator. So here we are at the man-in-the-middle position. We have seen that this information is going through the RTUs and come to the router. And here we can see a Wireshark window of it, and the actual packet here displaying that is a little over 14 megawatts. And the script changes this value to 11 megawatts, and this is being fed to the database, and the control algorithm sees this value inside. And what it means. First, we are going to add this man-in-the-middle type of attack, and here you can see the change here of the power unbalanced again, which is normalized by the microgrid controller, and which is fine. But if we get out from here, so we are removing this 11 megawatts, and the controller that instantly will see again 14.5 megawatts, the actual controller of the generator is going to be destabilized, so it gets out of synchronism, and eventually it creates a blackout event in this model. We are approaching the end of our time. I should summarize the main points. So today you have seen a cyber physical testbed, its theoretical background, and an actual implementation of it. Not just the testbed itself, but also there was some demonstration about high fidelity cyber attack scenarios. Today's key takeaway, I think, is this cyber physical power system model testbed with its approach to hardware in the loop, software in the loop, is a step towards a digital twin environment, especially with a cyber physical, a cybersecurity aspect. This was all achieved with the usage of RT-LAB and EXata CPS. This co-simulated cyber physical power system is relatively easy to modify and a flexible one. I have shown that adding a delay to this network is easy with just a few clicks. And at the same time, the same model is still being of high fidelity and making us available to do much more. So we can use our own tools, we can use actual devices, actual softwares on the same model with the same setup. And we can mix the two. So from this point on, we can freely decide what is being simulated or emulated and what is really there physically in the lab. And this can be changed on the fly also. So we can change with a simulated controller, with an actual controller. We can change a cyber attack from an EXata emulated attack to an actual attack, or we can use both at the same time. If you have any more questions, feel free to ask and feel free to contact me through email. And thank you very much for today's attention.
Thank you very much, János, for this great presentation and demonstration. I hope you all enjoy and saw how the University of Budapest is an advanced user when it comes to cybersecurity challenges for power system. Before answering your question you post in the chat, I would like to come back to a poll that we made at the beginning of this webinar. So just some comment. I think it's quite exciting to see your answers. So yeah, it's not a surprise because you attend to see the webinar, but yes, for you, cyber threats and cybersecurity is one of the critical issues that we have to face regarding power system development for now. It's also interesting to know that you are looking for a solution to simulate, as we presented today, a co-simulation environment for power system and both and communication network. And yeah, the third question was regarding how to implement this kind of which kind of testing approach which will be how to say the better one regarding the how to address these kind of challenges. And yes, you selected the real-time approach as the right one. So it's quite interesting to see that we have the same way or perspective regarding how to move forward on the cybersecurity aspect. And so for now, we are going to answer to your question. And so I will let Mehrdad to go through your question, and János and Mehrdad answer to it. So Mehrdad, please go ahead.
Yes, hello. Yes, we've received many questions, so I'll try to go through them as quick as I can. And if we don't get to any questions, don't worry, we can János will answer them after the webinar, and you will receive the answer. First question, János, is from Chamara. Is the functionality of the Raspberry Pi just to convert the data in the UDP packets sent by RT simulation to the IEC 104 protocol? I think they just want to know more about the functionality of the Raspberry Pi.
Yes. The main function is, yes, this protocol conversion, but it has other function as well. So it has some validity check beforehand. It sends the data to the other side. So these basic functionality were also modeled on these Raspberry Pis as an RTU.
Thank you. Suarali is asking about the communication network and the software used to model the communication network. You mentioned it's EXata CPS, but if you can maybe provide a bit more details about the tool that was used to model the network and the network itself, the communication network itself.
Well, it's a little hard to answer this question because EXata CPS is used for creating the network model. The plan for it, so what is actually being built in EXata and what is being built with VMware's virtualized environment, is based on our experiences with MVM, our partner in this project. And we used a mixture of them. So EXata CPS was for the high geographic distances. This is for the multi-layered subnets you were seeing in the demonstration.
Yes.
And inside the control center, the communication was simulated or emulated by VMware's virtual switch solution. So it was a mixture of those.
Those two. Thank you. Alok asked about if the RTUs or the delay caused by the RTUs in your configuration could impact the performance of the simulation.
Yes, definitely.
Mhm.
So RTU is also adding some delay to this whole setup, but this is the point of actually using hardware in the loop approach, since if we would have just a model, then there weren't any delay in the system. But since we added Raspberry Pi, we have some actual behavior for RTUs, and therefore the not perfect performance, some loss of communication if you wanted to model those ones. So yeah, RTU are really adding some delay to it, and it's much more than just having it as a protocol converter there.
Yes. And just on EXata CPS itself, can you mention why you chose that as the simulator of your communication network, or were there other choices but you went towards that? Because I think maybe we can provide more details about it.
Yeah. We have chosen EXata CPS on purpose. One of the reason using it was it could run on the same target as RT-LAB. So it has a complete solution. It is very flexible in a way that we can add virtual links through virtual interfaces between RT-LAB and the EXata CPS. And at the same time, it also allows us to add and map external nodes so that we can actually add actual equipment in hardware in the loop fashion to the simulation. And EXata CPS is very flexible tool, so we can really model the physical behavior, especially for large distance communication. So we can add delay, jitter, communication errors, and things like this. It is very easy to add those features with EXata CPS. So this is why we went with that model for the large geographic region.
Thank you. Also, what is the effect on stability due to the delay results? Or the delay attack, what are the effects of the delay attack on the stability of the model? I mean, you showed the results, but were they too aggressive, or?
There are some aspects which I can share with you. So with this delay, you have seen we have added a limited amount of delay to this network, and still it affected 200 milliseconds. It resulted in several tens of seconds actual response delay. So this is really the effect of this delay, but there are some other interesting cases which we weren't prepared to, or we weren't thought about that one before. So when we had started with larger delays, of course, okay, let's move it with 10 seconds and see what happens. And then we realized of the actual implementation, like we are using actual 104 protocols implemented, and it started to just time out. And that means we completely lost the communication between the RTUs and the control center. And it was a result of this delay, but not the expected one. So it's very interesting to have that one.
Great, thank you. Another question, does the brute forcing into the router mean you change software in the router, or do you modify a route so that you can get the data into a system that you can control and modify it before sending it to the end device?
We actually changed the software of the router in this setup.
Okay, that's good. Thank you. Can you, or how to implement a direct attack like the denial of service from the hardware setup that you have? Or have you done it?
Denial of service can be achieved multiple ways. One is using EXata CPS's internal denial of service attack. It works both on the emulated side, and it creates packets so that it could be seen outside. But of course, we can actually implement a denial of service type of attack from outside with physical equipments and actual tools. And in EXata CPS, we can create the queue length, how much packets could a node actually process. And yeah, so we can use denial of service both from outside and inside the simulation.
Okay, thank you. Another question, would the environment allow for testing different attack defense algorithms?
Yes, definitely. This is one of the reasons why we created such a complex testbed. These are the first results, and it's aimed to have a complete study system where we can analyze different kind of attack and defense mechanisms and try to implement like other cyber side related like probes, log collection, and see how we can defend ourselves against these types of attacks.
Yes. Can we encrypt the sensor data at RTU and decrypt before SCADA so that the delay and man-in-the-middle attacks are not possible?
In the current setup, we haven't applied any encryption.
Okay.
It is the use case with many industrial experiences. So no, we haven't applied encryption. And the other reason for not applying it is we wanted to check the effect of it. So if we encrypt it, then man-in-the-middle attack is not possible, of course, at least not on this scale. So we couldn't have analyzed anything. But on the other side, as I mentioned in the motivation at the start of the presentation, you can never be sure that there is no one in the traffic. So encryption is making things harder, but not impossible to actually decipher things or get the key or something else so that you can actually be in the communication even though it is encrypted.
Yes. One question is that many utilities use power system software such as PSSE and PSCAD and accept the results of these softwares instead of MATLAB. Is this version of CPPS able to use these software, or should it be redesigned?
RT-LAB is flexible. Our goal here was with a smaller network setup, so Simulink was easier to use. But HyperSim could also be implemented here. It is somewhat compatible with EMTPRV.
Yeah.
At the other end, we also have eFeatherSim, and those that is compatible with some other tools like what was mentioned here. So yes, we should change the model, but it can be adapted to larger networks and importing topologies from actual data. Yeah.
Yes, I should mention that since these kinds of questions have been brought up, the co-simulation platform that János is using is between OPAL-RT simulation tools like RT-LAB and the network simulation tool, which is EXata CPS. And EXata CPS, as János said, it can be used to model different types of networks and with different types of parameters and be used to initiate the cyber attacks. And the power system and the results can be seen at the same time on the power system side, which can be used, which can be made using RT-LAB. And in RT-LAB, there are different toolboxes, one of which is ePhaserSim, which can be used to model large systems, or just using MATLAB, which can be used to model microgrids like the one János used, or different types of systems. So that is a platform that is used by János in this testbed. Can we also create customized attacks after following MITRE, ATT, and CK? And how about the countermeasure selection?
Oh, I lost the letters. There are too many letters, and I'm searching for the question itself.
Yeah, I think we can get to that after. Is yeah, maybe we can get to that after. I can ask another question. Is the part of AMI advanced metering infrastructure where the smart meters communicate together taken into consideration in this test?
This is a different use case, so that is mostly used for, as far as I understood the question, that is more used for billing purposes and on lower distribution levels where actual customers connect to the grid. And this setup is focused on actual system operation. So here we are not using AMR, AMI, but direct connection with 104.
And just a couple of other questions. Just that, can we able to simulate coordinated cyber attacks? And can this testbed be used to use a different type of protocol, like a 6x50, for example?
Yes, we can definitely use other types of protocol, and it is very flexible since we can have actual physical equipment in the network. It's up to the equipment what kind of protocols can be used next to the built-in ones that is provided by the RT-LAB functionality.
Okay, and the coordinated cyber attack, for example?
The coordinated cyber attacks, yes, this is one reason of why we have chosen EXata CPS and why have I told about the possibility to use them together with EXata CPS and external real-life tools. So this is the next step. In the current project, our use cases were focused on showing a mixture of attack, and the next step is about coordinated attack. In the meantime, I have seen that, okay, this is about MITRE attack framework, the question was.
Yeah.
And for this result, it couldn't be fit in this slide, unfortunately, but these attacks that are not shown and part of what is shown, they are actually based on following MITRE attacks, pattern, techniques, tactics, and also with Lockheed Martin's CyberCure chain. Both were used with STRAD and DREAD analysis. So there are many more into this setup, but here we really focused on the actual test. But if you're interested, feel free to write an email and I can answer it in more detail later on.
Yes, and I don't know if we need to close or not, but is there a paper or is there any other website where folks can find more information about the testbed or about the studies that you have done?
The testbed is currently not published, so you cannot find it in a paper yet. We are preparing some papers, but it's not there yet.
Okay, so I'm told that we can extend 5 to 10 minutes. Yes, so a question says, can we introduce replay attack? How EXata CPS will be connected to OPAL-RT? So the connection between EXata CPS and OPAL-RT, as János mentioned, both of them are running on the same simulator, and the connection is through these virtual links. So on the OPAL-RT side, some virtual links are created once the simulation is running, and EXata CPS, those virtual links can be linked to the communication nodes on the EXata CPS model, and that's how they can be connected together. But can we introduce replay attack? I'm not sure what replay attack means.
Yeah, we can introduce replay attack. It basically means that we capture some packets and replay it back with some delay. Yes, absolutely, we can do that both with external tools, and as far as I know, EXata CPS is also capable to replaying PCAP files, so we can do it on multiple layers. Yeah, we can do that.
And the question says, why use the connection with simulation and communications with Raspberry Pi and not connected with EXata CPS directly? Can it be done with RT-LAB and EXata, or does it have to be done with HyperSim?
I'm a little bit confused about HyperSim, because HyperSim and RT-LAB in communication regards, it is similar with protocols and connections, so there isn't really a difference in it. We used Raspberry Pis on purpose because we wanted to create a testbed in which every element can be simulated or be an actual one, and so that we chose RTUs as a real equipment. But of course, we could have left them out from this simulation, but that would be just a pure simulation with no hardware. But in our case, we really wanted to add hardware in the communication layer.
Yes. And another question, can we update the control algorithm in the existing CPPS testbed and use a more accurate control system?
Yes, absolutely we can. Here our focus was more on the cybersecurity aspects. to create this environment. But as I have shown in the slides, you could see the control algorithm is actually running on a virtual machine. You can create as detailed as you wish. But right now we had only time for a simplified
one. One question is that if we consider network reconfiguration and implement, say for load restoration, and implement a hierarchical control structure with distributed secondary control, then how the delay would affect the stability, such as like small signal, large signal stability?
If you would change the model, it would change the behavior.
Yeah.
I don't have a specific answer for that. Most definitely, it would change the stability, and the delay would need to be had different or added to another node. But yeah, this is it. It depends on your actual model.
Yes, thank you. And lastly, we answer that as well. Can it be implemented? Yeah, I think. Yeah, I think we're good. Any questions that are left? We will send it to János, or either János or us. We can answer them and send it back to you. So thank you very much for all the questions, and thank you, János, for the answers and for the presentation.
Thank you very much, and you're welcome. See you soon.
Yeah,
Yes.
and please don't forget to answer the survey when you close the webinar. Just if you have asked for demo or if you want to see the upcoming webinars, just yeah, please answer to this survey. And yeah, thank you again, János, for this great presentation.
Thank you.
You're welcome. Thank you.